Welcome, everybody. Today is a pleasure to have Stefano Facchini as our speaker. Stefano, as he just said, is calling from Garching in Germany, near Munich, from the headquarters of the European Southern Observatory. Is 11 p.m. in Germany, so I would like to thank Stefano for agreeing to give the colloquium so late in the evening. Stefano graduated at the University of Milan in Italy in 2012, where he started working on the dynamics of protoplanetary disk using hydrodynamical simulation. After his undergraduate, he moved to the University of Cambridge to work with the group of Katie Clark, where he received his PhD in Cambridge in 2015. In that period, he focused on, he worked on studying the effect of star formation environment on the evolution of disk from a theoretical perspective. And after his PhD, he moved to Germany in Garching, where he worked with the infrared group at the Max Planck Institute for Extraterrestrial Physics, particularly with Professor Evine van Bisschok. And when he was there, he started working on the chemistry of planet formation, and also he got closer to observation. So he moved a little bit from theory to observation and started to use, in particularly, millimeter wave data to study planet formation. Since 2018, Stefano is a research fellow at the European Southern Observatory in Garching, which, for those of you that are not familiar with astronomy, is this international institution similar to CERN to some extent, that manage the biggest European telescope in South America. And at TISO, Stefano is using observational data across a wide wavelength range to probe the chemistry and the physics of planet formation. He also has some duties there. For example, he's helping out with the European ALMA Reduction Center, which is in charge of assuring quality of data before they are delivered to observers. And he's also served as an astronomer on duty at the Atacama Desert in Chile. So he has the privilege. I don't know, did you ever had the privilege to go there? I never had, unfortunately. I'm still waiting for
I did. It's wonderful.
So he had the privilege to go to the telescope, which in these days is not that all the astronomer can do. So with that said, Stefano is in between theory. He was born as a theoretician and has been moving to observation. And today he will tell us about his research during the last few years. So with that said, I'll give you the control. Are you sharing?
Okay.
You are.
Should be.
Yes.
What do you see?
Yeah, I see. We see your screen. Perfect. Okay.
Okay.
Now, before you start, so if you have question, if you need clarification during the talk, or if you have pressing question, I will like to ask you to put them in the chat, and then I will ask them to Stefano. Or as usual, if you can wait, we will have a standard Q&A session in the end, and then we will continue with our virtual wine and cheese until probably something like 5:30 here in Houston. And with that, I'm gonna shut up and give you the control.
Okay, thank you, Andrea, and thank you and the other faculty members for the invitation to give this colloquium. I had the pleasure to come to RISE, I think it was 3 years ago, to visit the Star and Planet Formation group there, and I love the place. So it's a pity I cannot be there today. As Andrea mentioned, today I'll focus on the physical and chemical connection between planets and their host environment and their birth environment, also in some sense, going from the very large scale to planet forming and even satellite forming regions. As we all know, for a long time, for thousands of years now, the only system, planetary system that the man had access to through our eyes first and then through telescopes was our own solar system. which is a peculiar one made of 4 rocky planets in the inner regions and 4 gas and ice giants orbiting at larger distances. And again, as you are very familiar with, this view has been completely revolutionized in the last 25 years or so, because what became more and more evident and apparent is that on average, every star, at least in the proximity of our own solar system, is surrounded and orbited by at least 1 planet on average. And making some kind of mind game, if we think that our own galaxy hosts about 400 billion stars, that would we have made the step from 8 planets known until 8 years ago to a fairly reasonable inference of about 400 billion planets in our own galaxy. And this is a total revolution from a scientific perspective, but also I think we may say from a philosophical perspective as well. So if we look at how the exoplanet discovery happened, I'm showing a plot where with the planet mass on the y-axis and the orbital distance on the x-axis. So throughout the whole talk, I'll use this AU astronomical unit as a distance unit, which is the distance from the star, from the sun and the Earth. That's what astronomers, what we do. I'm showing in yellow the solar system planets, and as time goes on, we see that from 1995, the first planet around the main sequence stars was observed, and then a large number, up to 4,000, roughly right now, actually a bit more than that with the TESS mission, we have seen a large number of planets. The most important message I want to give is that these planets are mostly quite different from the ones of our own solar system, and that was one of the major discoveries of these last years. And they're different in terms of orbital radius and mass, and in many other parameters that we're going to look into in the next couple of minutes. So if we have planets that have been detected through different detection methods, the first one is the transient method. So when a planet crosses the line of sight from the observer to the star, the star undergoes a little eclipse, and therefore the luminosity of the star drops, and we can therefore infer the size of the planet that is partially obscuring the star. So from this, we can get a radius of the planets, and if on the same planet we have a radial velocity detection, so we have a detection through the sinusoidal movement along the line of sight of the star that is being perturbed by the planet, we have a mass, and we can therefore put these planets in a radius mass plot, as I'm showing on the right-hand side here. And here I'm focusing on fairly small planets between, I think, 4 and less than 30 Earth mass planets. And we see different lines, and every different line shows a different bulk composition of the planets. And we see that there is a large variety of composition of these inner rocky planets. Again, showing a large variety that was unforeseen before these new detections and these new discoveries. At the same time, there's also diversity in the atmospheric abundances. When a planet crosses the line of sight again to the star, so undergoes during the eclipse phase, we can observe the transmission spectrum of the starlight across the limb of the atmosphere of the planet. And we can therefore extract a transmission spectrum of the atmosphere, which is informative on the chemical and elemental abundances of the material in the planet atmospheres. And if we look at both transmission and actually also thermal spectra of planets as they undergo a secondary eclipse, we see that, again, there is a diversity of atmospheric properties. Without going into details, we see planets as shown on the right-hand side that have thermal inversion in the atmosphere, like the Earth and the ozone layer, some that don't, some that have prominent water features, and some that don't. So again, we are at the stage at the first stage, which will increase enormously in the next years, of being able to probe chemical abundances in exoplanets. And again, they show a diversity. But where is this coming from? And this really the research I focus on. So these differences must mostly come from the formation processes where these planets are born. So the properties of the cloud where stars are born, then the properties of the disk that forms around newborn stars, where planets are born, and then the final processes of the disk dissipation in this dynamical and chemical trajectory, the properties of the final outcome of the planet formation, so the planets themselves, are sculpted. Throughout this talk, I'll try to emphasize and focus on just a few aspects of this physico-chemical journey from clouds to planets, because of course we could do a whole seminar course on this. And I'll try to span over different spatial scales from, let's say, 20,000 AU, the cloud scales, to disk formation region 500 AU roughly scale, and then to really smaller scale, we go down to actually a few AU, so few astronomical units in terms of spatial scales. So what about, I'll start with the clouds, and this gives me the opportunity to show this beautiful image. This is an image of the Orion Nebula cluster, which we can see still up during the night. We see both 4 very bright stars which form the trapezium, and this very bright star is clearly affecting some objects that are in the close proximity, at least on projected in the sky. And these are actually the structure where the first protoplanetary disks were darkly observed, or better imaged, in the 90s with the Hubble Space Telescope. So if we focus on some of these objects, what's actually happening is that the very bright star here, which is very hot, and therefore has a very strong ultraviolet radiation because of the high black body temperature. What's happening is that this bright star is impinging a small disk around a newborn star with strong UV radiation, and heating up the disk is leading to the formation of a wind. So it injects enough energy to have the material being able to escape the gravitational pull from the central star. And this leads to the formation of a kind of cocoon structure, as we can see in this kind of model. And I show here some beautiful new data that we obtained with these ESO telescopes in southern of Chile, where we observed one of these famous objects that was also observed with Hubble Space Telescope, and where we see the disk at the center, and we see the structure that this wind is leaving against the ionized gas in the area. From this data set, what we can do is we can get a spectrum at every pixel in the optical range, and we can therefore get the kinematics. We can get density structure looking at line ratios, and by doing this, we can try to extract how much mass the system is losing due to the external photoevaporation process. And this is about 10 to the minus 7 solar masses per year, which translating means that a 0.1 solar mass disk would be totally evaporated in about 1 mega year. So if planets forming here, roughly speaking, it has to happen fairly fast, within 1 mega year, where again, 1 mega year is fast in planet formation processes from an astronomical point of view. So we have evidence of how much this effect of disks being born in massive star forming regions has on disk and planet formation by looking, for example, at the disk mass as a function of distance from the ionizing external source. The disk mass here is probed by the millimeter thermal radiation of the dust. So we use this as a proxy for disk mass within some assumptions. And we see that in this particular case here, in this cluster here, this is actually the ONC, And in other clusters like Sigma Ori, for those who are familiar with these star forming regions, there is a trend of increasing mass with distance from the star. So systems that are born close to these ionizing stars are being evaporated, and we have evidence of that. But not only this effect from clouds affect disk evolution. If we look at some hydrodynamical simulations, I'm showing different zooms of a hydrodynamical simulation of a star forming regions. So there is a large cloud of gas. This cloud then collapses in different clumps. And I'm zooming on different clumps of the star forming simulations. And what we can see is that as stars are formed and disks are formed around them, these systems are highly chaotic. And we have a lot of interaction between different star and disks. And this can, again, affect and impact the evolution and the planet formation potential of planet forming regions. Again, recently we had, I think, a beautiful confirmation of this in different observations. I'm just showing a particular one where I'm showing an infrared image of this is the SU Auriga, for because I know some of you are interested, system. So at the center, we have a star, we have a disk, and there are filaments that are traced by infrared radiation that is being scattered by small grains, this starlight being scattered from small grains present in this structure here. So this doesn't look like a nice disk. So something is happening. And if we combine this with kinematical analysis of some gas data that we had at the same time, and we look through the structure of the gas, we can actually reconstruct the whole 3D geometry of the system and understand whether the gas is accreting or being ejected. And this shows that there is material that is being accreted today onto disks. So the chaotic environment where disks form can still accrete material even at quite late stages and impact the mass and angular momentum history of these disks. Another case, I'm showing here again an observation. These just focus on these two are two disks that I'm showing here with the pointer. They are rotating, and therefore we see these blue and the red features. So we're tracing with Doppler effect, we're tracing the velocity of the system, and we see a huge spiral arm. The spiral arm, by comparing this spiral arm with hydrodynamical simulations, what I showed is that this can be clearly produced by an interaction, a violent and impulsive interaction between a star that passed by and the star already hosting a disk. The gravitational pull, the tidal force disrupted the disk, creating these huge tails. And again, as evidence that these things happen, and we need to take them into account when we try to understand planet formation. And why I think this is very relevant is because actually most stars are formed in high density, high radiation environments. These are usually not looked into too much because they're very far from us, so difficult to observe. But this bottom right part of the plot with high irradiation and high stellar density is actually what creates most of the stars and therefore planets. And if we want to compare mature exoplanet population to disk formation, we need to look into this area here. In particular, this red area and this blue area are regions of the parameter space where the disks are being totally destroyed and evaporated in less than 3 mega years, so fairly fast. And I'll leave this to the end, but this poses some questions that I think are very interesting. Is how common are these late infalls of material that I showed? So how common the mass of planet forming regions is replenished by the environment? Or how much does external photoevaporation affect disk evolution, for which we have some evidence, but how much really and how does it affect disks in very massive environments? and how frequent are these star disk encounters in close by, because these seem to be way more common than we thought earlier on. And these are just some of the questions that I think are plenty very open and for which there is a lot of space to work on, to try to understand what the answers are. But what's intriguing is that if we scaling from this cloud kind of spatial scales, if we start to zoom in, and we zoom in as much as we can, pushing our instruments to the best angular resolution we have, and we look into one of these regions, these are low star forming regions in Taurus, in the Taurus constellation, what we see is that actually these disks are very well ordered and structured. Even though they're surrounded by a quite chaotic environment, many of these objects, at least in the low star forming regions we have close by, are very ordered. If this is a common feature, this again in the top part, as the image I showed before, is tracing the millimeter thermal emission of dust grains. Whereas in the bottom part, I'm showing the scatter light in the infrared scattered by small micron-sized grains. And we see that these disks are very ordered. They have very ordered features, mostly gaps and rings in here, but also spiral structure and kind of shadows that I won't go into detail. But so the question immediately is what could be the origin of this? And of course, a lot of work has been done on this, so I won't focus on it too much. But one of the ideas, which is probably the leading one in our community, is that this structure are caused by planets that are embedded in their environments, as in these hydro simulations, where a planet clears a clear gap in the gas surface density within the disk. And creating this clear gap also creates a pressure maximum outside the orbit of the planet. And due to a aerodynamical drag, the dust accumulates naturally in this pressure maximum to a physical phenomenon that we call radial drift. And that what leads to the creation and to the genesis of this gapped structure. But the question is, are we really sure that these origins are, that these gaps and spirals are originated by planets? Because there are many different physical mechanisms that can in principle create some of these structures. And there are many people in our community that reasonably so do not believe that all of these structures are caused by planets, because there would be too many. So I'll focusing again on the planet disk interaction is what is another observational way to say if there are planets embedded, and that's something I've been focusing on lately quite a lot, and that actually planets embedded not only leave and imprint the disk morphologically in their dust emission, so just basically sculpting the density structure, but orbiting, they also perturb the kinematics of the gas in the proximity of the planets. And if we have very good observation, in principle, we could try to observe these, what we call spiral wakes, so the perturbation that the planets creates in their disk, and therefore infer the presence of the planet by kinematical mean. This is something that is fairly new in the last 2 years. The community is really pushing for it. And this is just one example where here we have a kinematical maps. Here we have blue shifted and here red shifted gas. So the disk is orbiting, and that's why we have this strong blue shifted and red shifted sides. And if we subtract a model, a simple model, like a Keplerian model, so with very simple physics from it, doing a fit of this image, we get some very strong residuals that are very localized in radius and azimuth. And this, for example, is very promising in inferring the presence of a planet that was only purported before from the dust morphology. I can show one particular case I worked on. This is a CQ tau disk, where this is the infrared image where we see spirals. This is the millimeter emission tracing the larger grains. Again, you see that there is some maybe spirally thing. There is some structure in it. But if we look at the gas, again, I think there is a lot of information that that we can acquire. Here I'm showing the this, we call it a brightness temperature map. So what I'm showing here is the intensity is the peak intensity of the CO of a carbon monoxide rotational molecule. So this is the 2-to-1 transition. CO has a very strong dipole moment, so it has a very strong rotational Einstein coefficients for rotational transition, and therefore it's very easy to observe at millimeter wavelengths. And here, here's the map of the CO emission. If I remove an azimuthal average of this emission, I can clearly see that a spiral pops up in the CO, in the brightness of the CO. But not only, if I take the kinematical map, similar to what I've shown before, and I subtract a simple Keplerian model, again, I see the same spiral I was seeing in the CO intensity. I saw it also in the kinematical residuals. So this shows that there must be a perturbing body, also fairly massive. We don't know its exact location, but there must be a perturbing body that is imprinting the kinematical structure of the disk. And I think this is a field where there is a lot of space for improvement in the next years. So I showed so far that, okay, so if these disks that I'm showing on the right-hand side this is an actual image of, again, the CO of a disk. The data are actually from Andrea. If these disks host massive planets, these planets alter the structure and the dynamics of the disk itself. And that's how we can infer if they're present or not in these objects. But at the same time, the hosting bodies, so these protoplanetary disks, are the environments that determine the mass, the orbital radius, the multiplicity, or the orbital architecture of the final planetary system you have. And in particular, and they're going to determine the chemical composition of the planetary atmospheres of the planets that form in it. So if we want to try to link and the host environments to mature exoplanets, I think one leading way in the future is really trying to link the chemical properties of the host environments to the chemical properties of disks. And again, yeah, chemistry. So why, of course, this is why is it interesting is because it's have already evidence that chemical complexity starts at the star formation phase and goes all the way through the planet formation phase, leading to a fairly, I think, unexpected complexity already before planets were born. So in star forming regions, we have, you know, from fairly simple molecules, but we have radicals like hydrogen cyanides with that formaldehyde. But if we start looking at our own solar system in the pristine material that form like the Earth, we start seeing amino acids in comets like glycine or glycoldehyde, and in meteorites, even guanine or adenine have been detected. And so the questions we're going to ask is, we have seen that these disks are present substructured, but how do this substructure affect the chemistry of the planet forming material? Oops, sorry. And the dust substructure affect my pointers got crazy. The substructure in the dust continuum affects the chemistry in a large variety of ways. It affects the dust opacity, so it affects the temperature. It affects the gas grain coalitions. So again, it affects the gas temperature and how the dust and gas are balanced. The dust leads to the formation of H2 molecules. It leads to the hydrogenation of simple atoms and molecules into more longer chains, like the ones I showed in meteorites and comets. So there must be a very strong interplay between the substructure in the dust and the chemical complexity. And this is extremely important because it is within these gaps, it's within these substructures that planets are accreting chemically enriched gas that is going to determine their final atmospheric abundances. So without going into detail, but from doing thermochemical models, I showed that these dust substructures do clearly affect the composition of the gas and solids in, for example, gaps. What I'm showing here is radius. In all planets, we have the radial direction in a log scale of a pluriplanetary disk. In a U, again, in the vertical direction, I'm showing the height above the disk midplane. So there is a planet here at about 20 AU that is clearing a deep gap, as you can see in the density of the gas. As if we start looking at different chemical tracers, we see that, for example, the ice abundances or even electron abundances or ionization are altered by the presence of this gap. So within these gaps and within these rings at the edges of the gaps, we have strong thermal and chemical gradients that we need to understand how they affect the chemical abundances of accreting material. This is something that has been observed in a bunch of disks, some chemical substructure in some molecules like DCO+, CN, formaldehyde, and this is a small hydrocarbon, C2H. But what we want to do and try to do is really make a strong connection between this chemistry, chemical morphologies, chemical properties, and accreting planets. In order to do this, I'm going to focus quite some time on one particular source. Again, Andrea is very familiar with it, which is PDS-70. It's one object, one disk. And this one disk that you can see here in the infrared hosts two massive protoplanets. One is PDS-70b here, clearly visible in the infrared, the thermal emission of the planet or of circumplanetary dust. And then the second planet is here. These planets are accreting, and we see it because we see H-alpha emission. So we see atomic hydrogen emission showing gas that is violently being deposited in the proximity of the planets. We also see some circumplanetary dust material close to the planet that was first discovered by Andrea last year. And we see some kinematical features in the proximity of the planets. So everything that I talked about so far, substructure, kinematical imprint, massive planets that are accreting material, this is the only system where we know that this is happening and we have direct observational evidence of it. We have also evidence of their orbits, which is super important to have a coherent picture. This is I'm showing here the astrometry, so how the planets move during years around their star as our solar system planets orbit around the sun. These two planets are orbiting around their central star. And these are gravity, which is a infrared interferometer. So it's a technique that allows us to have a very exquisite precision in how these planets move. And you can see the arrow bars in here, which are about 100 microarsecond for the astronomers here. And from this, we could constrained very strongly the how the planets are orbiting as they are being formed. But not only, we also tried to get spectra of the two planets, and we did. This is a low resolution spectrum, around between 2 and 2.5 micron. And we didn't see any prominent molecular feature, probably because the dust was obscuring the actual planets. And therefore, we did not manage to get any clear idea of, for example, the elemental abundances in the planet atmospheres. So let's have a better look at the system. Again, here I'm showing the millimeter ring. I'm showing here the map of the CO, where we see a gap carved by the planets orbiting the central star. We can also see the kinematics. I think these images are just wonderful, how well we can trace this. And here I show again the CO emission, where in a slightly different way, showing the peak intensity of the emission, so the temperature of the gas, really. And what we can derive from these two plots is that is the whole 3D structure of the disk. So we can trace that this disk has a very conical shape. But the question now is really, we see these two planets, we see they're accreting, we see how they sculpt the disk, we see how they kinematically perturb the disk. We know they're there, everything works. But the question is, what are the elemental abundances of the gas that is being accreted by the two planets? And secondly, how does the dust substructure that we see, this beautiful ring and millimeter wavelength, affect the molecular abundances? To do this, I collected data again from ALMA, the millimeter interferometer in Chile, which I had the luck to go observe with physically. And these are maps of different molecules. We have CO isotopologues, we have ions like HCO+, we have small hydrocarbons like C2H, we have sulfur-bearing molecules like CS, and we have cyanides like DCN and H13CN and others. These are the first maps of the chemical inventory of a disk that is known to host protoplanets. If we try to extract the flux, we can extract fluxes. Here I won't go into details, but we have some more molecules that I didn't show before that were not very clear. We have either hydrocarbons, for example, that are very important. The cycle is C3H2. And we have strong upper limits on some molecules which are important, like sulfur monoxide, SO. And I'll show in 2 minutes how important that is. From the beautiful maps that I showed, we can actually extract column densities. We test some method using the extraction method, the column density, looking at different hyperfine transitions of the C2H molecule, and they agree all very well. Here is the column density. Here, the bottom is the optical depth of the line. And we can do it for all the kind of molecules we image well. And therefore, we have a direct measure of the abundances of these molecules in the disk. So with these numbers here, we can then look at the carbon to oxygen ratio of the material. And I'll show in a second why this is important. But the carbon to oxygen ratio is a very important parameter that regulates what can happen in an exoplanet atmosphere. For example, if thermal inversion can happen or not, how much hydrocarbon. But to make a long story short, how quickly and how far you can go with organic chemistry you can have in these atmospheres, because the more carbon you have free from the CO bond, the carbon monoxide bond, the more quickly you lead to organic chemistry. So if we look at we focus on the column density ratio of CS over SO, these two molecules. If you remember, SO was not detected, called the sulfur monoxide. For typical carbon to oxygen ratio, or like solar carbon to oxygen ratio, we should have that the SO is way more abundant than the CS, but that's the opposite of what we see. So we would expect the density ratio of about 3%. What we see is a ratio that is above 100. So what this means is that we have extremely high CS abundance over SO, which can be explained only if there is a very high carbon to oxygen ratio gas in this disk. So the material that is being accreted by the two planets is very rich in carbon compared to oxygen. And we can do this also by looking at other proxies. I'm showing on the y-axis the flux ratio of a line of these given molecules over 13CO. This is just to have a normalization. And I'm showing how these lines, we can focus on the C2H here, correlates with the carbon to oxygen ratio. So we go from 5% to about 1.5. And we can see that the hydrocarbons, the C2H and cyclone C3H2, strongly correlate with the carbon to oxygen ratio. If we look at PDS 70, the measure of the C2H over 13CO flux ratio is here. And again, this can be explained only if there is a carbon to oxygen ratio that is larger than 1. Again, indicating the chemically enriched and chemically processed material that is hosting these disks. This, I think, is the first. This is instead, why is this carbon to oxygen ratio important? Because if we look at planets, we can actually derive the carbon to oxygen ratio within the planet atmosphere. And with huge error bars, but there is a statistically significance once we look at this sample. There is a significant result that the carbon to oxygen ratio of the planet atmospheres are higher than the carbon to oxygen ratio of the hosting star. And this must be due to chemical processes and accretion processes that happen in the disk. And understanding what is the chemical abundance and elemental abundance of the material that is being accreting onto these planets is what we need to do if we want to link chemically the host environments with the exoplanetary atmospheres as they're formed. The final points, and then I'll going at the last 10 minutes or so, so I'm going towards the end of the talk, is to, again, look at the radial profiles of some of these molecules. I won't go into a lot of details, but what you can see is that different molecules show very different profiles. In gray, I'm highlighting where the continuum is peaking, so where the dust is peaking. In the dashed black lines are where the planets are. You can see that different molecules peak at different radii compared to the underlying dust continuum. And this must be due to a physical reason. Was there a question or no? And in particular, what I'm showing here is where the emission profile of the lines peak in radius. So these white dots here with associated error bars is where the radial profile of the lines, of the different molecular lines is peaking, as compared to the continuum, so the dust emission profile that I'm showing above here is in orange, and below here it's color-coded. It's the same profile, just color-coded, and here showed in 1D. Here in gray, I'm showing the profile of the infrared emission instead. Actually, this infrared, infrared emission in K-band observed with sphere, that we see that is not exactly cospatial with the millimeter emission, but this is expected actually in these harboring planets. And we see that the lines peak at very different locations systematically. And this plot, I think, is very informative. And I think it shows what we can start to do. This is just the first time we try to do this, but what we can start to do when we look at this kind of data quality. So for example, if we look at the 12CO, what we're seeing is that we're tracing, where the line peaks, we're tracing the density increasing outside the gap covered by the two planets. That's because it's a very highly optically thick line, and so it's peaking closer in. If we instead look, for example, at more rare isotopologues of CO, like 13CO or C18O, we see that the peaks are more towards where the millimeter emission is peaking, and these are actually probing the pressure maximum outside the orbits of the planets. So they're probing the bulk density of the gas. If I look at HCN isotopologues, these are again peaking closer in, and that's because the formation of HCN is led by strong UV irradiation from the central star. And so again, they're peaking closer in. They're showing the radiation pattern on the disk, similar to the ions that show where the cavity wall covered by the planets is impinged by X-ray photons from the central star. So for some people, also in the audience, we're tracing the PDR region at the cavity wall of the disk. So we can, within this spatial information, we can also do some very nice things, also thinking about the relation with our own solar system. For example, using different lines of the formaldehyde, H2CO, we can extract an excitation temperature of the molecule. So we can extract the kinetic temperature of the gas, assuming it's thermalized. And we see that this molecule, and therefore the gas, has a peak temperature roughly where the millimeter emission is. So where this arrow is pointing to. At the same time, if we try to derive the deuteration of the hydrogen cyanide molecules, we see that there is a peak in H/D exactly at the same spot. So there is some temperature effect that is affecting the D/H ratio profile within the disk. And I think this is beautiful because we're really looking at chemistry happening on the fly in this planet forming gas. And that's just this simply explained. I mean, I know maybe not many people are familiar with chemistry, but it's fairly simple in the sense that it's just Hd, which is the main carrier of deuterium, that it reacts with the abundant H3 plus, and this goes into H2 plus H2D plus. This reaction, this is usually a closed loop, but what happens is that below 30 Kelvin, the backward reaction is quenched. And that's because the H2D plus molecules has a way lower 0 point energy than the H3 plus. So below 30 Kelvin, you cannot go back. And this H2D plus is what carries the deuterium atom into organic molecules. And that's exactly what we see. As we hit temperature, basically below 30 Kelvin, going farther from here, we start seeing the H/D dropping. So we're really seeing chemistry on the fly. At the same time, very quickly, because I'm running a bit out of time, is that we can do this both for D/H, which is very common. So the deuterium fractionation is something that is commonly accessed also in the solar system, but we can also do this for other isotopes. For example, nitrogen. We can look at how the 14N/15N ratio within the hydrogen cyanide molecules varies with radius. And again, we see a trend. This is direct evidence of the temperature and density structure of the disk altering the fractionation of these molecules throughout the disk. So chemistry does happen in disk, and chemistry has to be taken into account to interpret exoplanetary atmospheres. So going towards the end, I mean, this is just a summary slide of what I've said so far about PDS-70 in the sense that, to me, it is outstanding and just mind-blowing that nowadays we can directly observe embedded planets emitting in their thermal radiation. We can see circumplanetary material that is probably forming moons and satellites around them. We can see how this sculpt their systems, their hosting disk in their density structure and the kinematics, again, linking these two. And to me, it's even more exciting that on these objects, we can directly access the chemical abundance of the planet forming gas. And to me, this means it's opening a new era in the planet formation community of being able to really connect the planet formation stage to atmospheric abundances of mature exoplanets. So said this, I would, what I really try to convey, and that's my aim also for the future, is really to try to have a coherent picture from star forming region to planet properties. And to do this, I'm showing this crazy busy slide, which is slightly biased towards more ESO instruments because that's where I'm working right now. But to say that the future is looking great in terms of observational facilities to probe different processes at the planet formation stages. We can probe inner regions through spectroscopy, through interferometry, as I showed. We can probe the bulk density of the planet forming material with the millimeter interferometers or centimeters interferometers like the VLA. We can probe the scatter light like with SPHERE or GPI, and in the future with GMT-IFS. And also very interesting for me is that we'll be able to directly trace more and more of these planets by looking at more mid-infrared, particularly radiation, which is where their black body is peaking because they're fairly cold. And this is happening in 1 year from now. This will happen, roughly speaking, with JWST, with GMT in the more far future, with ARIES in the near future, with ESO, and with different instruments. And again, I think we do have in the upcoming future, and also right now, the observational facilities to probe and to have a coherent picture of all these processes. And to conclude, instead of having a summary of everything I said, I'll extract and use what I said to say 4 main points that I want to focus on in my upcoming and future research. And the first one is really to manage to probe the effects on the environment, on disk evolution and planet formation. And this can be done. And I also know that at RISE right now is something that people are doing, but probing the effect of environment on the planet formation using a variety of observational facilities, and also with theoretical development as something as I've done in the past. The second is that I want to determine the chemical evolution and the chemical abundances of planet forming material. And this can be traced from early phases of planet formation to planet hosting regions like PDS-70. Because I think this will link and will connect all the physico-chemical journey from the clouds to planets. And the third point is that I'm really looking forward to also characterize the kinematics of planet formation, and this to really understand how planets accrete their gas. So to be able to trace their accretion by tracing the kinematics of the gas while we trace their chemical properties. And again, this is something that I think has a very bright future in upcoming years, in particular thanks to ALMA at millimeter wavelengths, but also thanks to other instruments like GMT, which is and ELT, so 30-meter class telescopes in the future. For example, using the CO vibrational bands close to the star and mostly close to the planets themselves. And finally, I also hope in the future to at least collaborate with also faculty members, but also to push for my own research programs, as I'm doing with JWST, to detect and characterize young planets as they are embedded in their disks. If we manage to combine the chemistry, kinematics, and direct detection of planets, I think this will really probe a coherent picture of how planets accrete their atmospheres and what is the properties of the gas that is being accreting and determine the final outcome. So I think this is being and showing what a bright future we have in this community. So I feel lucky to work in this particular field, and I really look forward to work on these coherent and cohesive projects in the next years. And with this, I'll conclude and take any question you might have. Thank you.
Thank you, Stefano, for the great talk. I'll clap for everybody here.